Okay, we are back. It is 10 a.m. Thank you again. We're coming back online after a brief break. So Universal Robots, you probably all heard and know about Universal Robots today. Obviously, it's one of the most revolutionary products in the last decade for industry to allow to do jobs right next to people that you weren't able to do before. However, UR has not stopped at that. Today, you're going to learn about another product from UR that's not a robot, but enhances the robot in feeding. And with us today is the product manager, Eric, from UR ActiNav, and he's going to share that with us.
All right. Thanks you for that introduction. Yeah, welcome to everybody online as well. So today we're going to talk about ActiNav. ActiNav is, we like to not say bin picking, although it is a loading machines from bins product, and I'll explain the distinction that we're making with that here. So what we're going to talk about is, first of all, our manufacturer is looking to automate machine loading. I think most of that will be pretty obvious to all of you. What technologies are available? You know, there's a lot of alternative technology. The right technology is just as important as learning about all 5 of them. Why would you from bins? Why would you choose to automate your machine loading from bins? Why ActiNav? We'll go through some customer stories, and then of course, you know, how we can help you. So we'll spend the next about 30 minutes here with you. So top reasons why customers are looking to automate machine loading applications. We really hear 3 things over and over again. You know, no people, got to reduce our costs, and increase our production capacity, particularly in 2nd and 3rd shift, you know, when nobody else is around, or if you're not running a 3-shift operation. Typical stations that we're looking to automate, you know, one of the things that's funny about machine loading or machine tending is the first thing people think when they hear machine is CNC machines. And we absolutely do feed CNC machines with ActiNav. But a lot of what we feed are what our customers call what you guys might refer to as stations. Test stations, nut welding stations, turntable stations, drilling or tapping or polishing stations. We refer to all of that. All of that we include in what we call machine loading or machine tending. So this is what I like to call the automation engineer's tool chest. You know, you have a station you want to automate, and you need to pick one of these 5 technologies. The interesting thing is, in the world of machine loading, is there is no one perfect technology. You're going to see in the demo room, there's the flexible feeder with the Epson robot with the SCARA right next to the Universal robot picking from bins. And both of those are great technologies. We're not here today to tell you that, you know, this one technology out of these 5 is the perfect for all situations. They each have their pros and cons. They each have their strengths and weaknesses. What we want to share over 5 minutes is a little, you know, kind of high level about how, you know, what are the big pros, what are the big cons, what's the best time to use each of these technologies, and then we'll really dive into when do you want to choose to load your machine from bins. What's that criteria look like? So your options are, you know, bowl feeders, parts on conveyors, parts on trays. You know, you got the flexible feeders, and then you got your picking from bins. So let's go through those one at a time here. Bowl feeders, pretty well known. They're certainly the fastest of those 5 technologies. They're going to singulate parts. They're pretty cost effective for small parts. You know, when you get down to a variety of parts, though, usually bowl feeders are hard tooled for just one part. So if you're trying to do something with more than one part, you know, they're not particularly flexible. You know, the larger the parts get, you know, bowl feeders can get, you know, $50, $75, $100,000+ when you start to get into the larger size systems. So really good cost effective for small parts, especially for one part. They're certainly the fastest, but you know, they have some limitations as the part size increases, as the part variety increases, and you know, bowl feeders being mechanical things, you know, they break and need maintenance, and you know, and they make a lot of noise. So good, you know, good pros and some cons as well. For part trays, here at Universal Robots, and we love part trays, we should say. A lot of customers, machine loading is, either our number 1 or our number 2 application. The reason is retrofitting existing station cobots to the front of them, regardless of which of these 5 technologies you're choosing. Cobots are safe or can be made safe around people. You don't have to cage them. You're not typically deploying a brand new cell. So cobots have a lot of benefits in general towards machine loading. Part trays, absolutely the simplest implementation. Put some cutouts to locate the parts, and Universal Robots makes it really easy to program, picking up from A1, load, unload, put it back, A2, load, unload, A3, et cetera, et cetera. So very easy, cost effective, because it's basically, just the cobot and end effector, and it's the lowest cost option here. But they're really ideal for long processing time applications. If your cycle times are greater than, let's say, 5 minutes, if you have a machining process that's 5 minutes long and you lay out, 50 parts, it's going to run, 4-5 hours of processing time before that tray needs to be refilled. So that's a really good application for trays. On the other hand, if your machining time is 30 seconds or 45 seconds, and you lay out 50 parts, and you have to refill the tray every 20 or 30 minutes, why'd you automate in the first place? I had somebody tell me, if I have to get an operator to do something every 45 minutes, an hour and 50 minutes, the reality is every time I go out there, the machine's sitting idle. They're not going to do it. They're busy, doing what they're doing. The task takes 5-10 seconds that they're doing repeatedly. So the relatively infrequent, once an hour, once every 45 minutes, just really hard to get that to happen. So as the cycle times get shorter and shorter, trays start not to make sense, perhaps. The other thing is, depending on the cycle time, you're not going to get that off hours, second and third shift type operation. They're not going to run very long, depending on the cycle time into third shift. They can also be, fairly labor intensive, depending on the size of the part and the trays. If you're processing 2 or 3, having 3 different trays with different cutouts is reasonable. If you're processing 25 different parts and you need 25 different trays and it takes 30 minutes or 45 minutes to load up the tray, you haven't really solved the challenge you're trying to solve, which is to reduce labor to almost 0, right? Trays, we love trays. They have pros, they have cons. Great for long machining times, very simple to set up. But as the cycle times get shorter and shorter, they have to make sense. The other thing is that, of course, with a tray, you're limited by the reach of the robot. How many parts can you pick? Depends how long of a robot arm you have. Right? That's sort of solved with conveyor belts. So conveyor belts solve one problem of trays, which is you don't have the robot reach problem. So with a conveyor belt, the parts, that means you can usually use a smaller robot, perhaps with less reach, because you don't need the reach to get all the parts on the tray. The challenge sometimes with conveyor belts, though, is that it really only works with limited part types. It's usually hard-tooled for one part type, so again, you're not getting that flexibility typically. And the second thing is the parts have to stand up on their own, because if they need to singulate to a point at the end, complex geometries, brackets, things that flop over don't work well. So conveyor belts can get you that extended longer than a tray. They only work for typically one part and a subset of part types. And of course, obviously they're long, so that takes up. Okay, so then we get to, and I put all these together, although there are unique differences between them. Vibrating tables, flipper tables, backlit tables, and flexible feeders. And there are distinctions between all of them, but they're similar in that they all use a 2D camera, separate the parts or flip the parts into the correct orientation, and then 2D vision tell the robot where to go and pick those up. Very well suited for small parts. certainly of all these technologies, bowl feeders or flexible feeders for small parts is going to be the way to go. Washers, screws, O-rings, all that kind of stuff. Flexible feeders are the way to go. As the parts start to get larger, and I say larger, I mean larger than, let's say, 3 or 4 inches, maybe up to 5 inches, it really doesn't work. You're talking a lot of vibration or flipper action to get parts to move. So as the parts get larger and heavier, it just stops being effective. The other thing is that generally it's used for assembly, not machine loading. And of course, in this presentation, we're talking about options for machine loading. So it can be used for machine loading, but often it's more targeted towards assembly. So yeah, so nice pros, not so good for larger parts, heavier parts, and there's a lot of different options to have different, tray materials, different tray orientations. There's a lot of combinations to get it just right. But very good technology and also used with cobots. So hopefully that gives you a little overview of kind of the 4 available alternative technologies to what I'm now going to present to you, which is loading machines from bins, which also has its advantages and its disadvantages. First of all, fundamentally, nothing holds more parts than a bin. So when you're talking about longest unattended runtime, the best option for the longest running machine loading system is to load parts in bins. Bins also have the advantage of having the lowest labor content of all of those. With a tray, you have to have somebody, arrange and orient the parts, right? With a bin, you'll see in some of the videos, that is the extent of the labor, which makes it very attractive. Because in this market, with such a labor shortage, having almost all labor, not required to run the system is really, really helpful. And then, the second main reason why people choose to pick from bins is part variety. A lot of those technologies that I mentioned are either hard-tooled for just one part or have limited part variety. I can tell you most of our customers have what I call medium mix when they use ActiNav, which is typically somewhere between different parts per station. If you're talking about hundreds of SKUs, it starts to get a little cumbersome, I would say. So most of our customers have between 3 and 20 different parts. And we'll show you in the live demo here how easy it is to get new parts once you have a work cell up and running. The downsides, it's only the most expensive of all the 5 options. You're getting, extended runtime, increased production, eliminating almost all labor, but there's, of course, a cost to that with 3D vision and motion control. There's an inherent limitation with bin picking is that only certain part types work. There is no suck grip mag end effector, magical end effector. If you need a different type of end effector to pick a part on the left side as the right side as the top side, that such a thing doesn't exist. So the parts have to have a geometry such that you can use one type of end effector to pick it on all sides. Flat parts, you have to pick on 2 sides. 3-dimensional parts, you have to be able to pick on at least 3 sides. Cylinders, you typically only need to pick on 1 because they're symmetrical. But you generally need multiple pick points, and that means that the part geometry itself has to lend itself to it. Another limitation is what we call monkeys in a barrel, right? Parts that hook together. If you go in for one part and you pull out 4, it's not a great, that's suited to bin picking. So there's only certain part types that are well suited to bin picking. So that's one limitation. And then one limitation that has historically been a problem, but which I will show you now is not, is that, loading from bin, it historically was very complicated and very hard to make all these things work. Very time consuming. Talk to some integrators, hundreds, perhaps even 1,000 hours of integration to get, to talk to the robot with all the programming associated with it. And that's not the case here. So, but for generally picking from bins, that was a consideration before. So if we sum all that up into just like 2 words each, flexible feeders really good for small parts. Bowl feeders really fast. Conveyor belts and trays, trays really good for long machining times, little variety. Conveyor belts, very simple, but only a certain subset of part types. And then with bins, absolutely the longest unattended running, nothing holds more parts than bins, absolutely the lowest labor, and medium flexibility. Like I said, 3 to 20 parts. We do have customers doing more than 20 parts, but not in the hundreds, right? So let's deep dive into that now. So you notice the title of ActiNav, or the subtitle, the byline, is Next Generation Machine Loading. So what is Next Generation Machine Loading? Why do we call ActiNav Next Generation Machine Loading? And it really has to do with these things. One, what are the needs of our customers? They need super long unattended run times. They need a system that they can set up, that they can put a bin of parts in front of and not have to mess with it. It shouldn't stop for any reason. It should just run for a very long time, lights out if possible. It should be reliable, collision free. It should not stop. It should have super easy programming. You shouldn't need to spend hundreds or 1,000 hours of integration time to get the system up and running. It should be very easy to set up. It needs that flexibility, so easy part changeover, easy part programming, and the last thing is it should, have absolutely the lowest labor content, because that is a key problem that people are trying to solve. So that's why we call it next generation machine loading. But as we've seen, all the technologies have their advantages and disadvantages. I can tell you where it fits. ActiNav is absolutely fantastic. It solves a problem that no other technology solves. So a little bit about ActiNav. So ActiNav from Universal Robots combines 3D sensor, motion control, and the robot into a pre-integrated kit that's designed and tested to work together. And that's completely different than every other 3D camera that's designed only to take pictures and find parts. Taking a 3D picture and locating parts is table stakes. That you have to know where the parts are, but that's not the problem. The challenge is to make the system run for a really long time and be reliable. And so that's where the motion control comes in that ties it all together. So being from Universal Robots, we've pre-integrated all that together. We have vision system, we have CAD matching, so that finds the parts. We have the motion control that you don't have to program all of that. The system figures out how to reliably move throughout the space to pick and place the parts out of the bin and into the machine that you're trying to load. So because of that, we say it's certainly the most reliable of bin picking options. It's the most flexible, pre-integrated, definitely the easiest to use, and very fast to program. And we'll get you some hands-on time out here in the demo. And like I said, machine loading from bins rather than bin picking. It's a distinction maybe we make. Okay, so what is this path planning stuff? So first of all, there is 20 years of path planning, proprietary path planning technology built into that black box, into that autonomous motion module that allows this system to figure out how to move through the space. There's space in the world that their only business is to focus on path planning, and Universal Robots acquired one of those companies, I think 5 or 6 years ago, one of those 2 companies. And so they started off with NASA and undersea submersibles and surgical medical robots, really advanced robotic motion control things. And we've taken all that technology, those algorithms, and built it into ActiNav. But you don't need to be a PhD roboticist or a vision engineer in order to use ActiNav. We've leveraged that technology to make the system reliable and simple. So that's what's inside the AMM. Yeah, it enables the reliability to pick more parts out of the bin. So our bin yield with ActiNav is typically a lot higher. If you look at a typical, kind of 3D camera demo, what you'll see is usually a long straight end effector, maybe this long. I like to call these stab and grab. because you'll see they're trying to keep the robot out of the bin. Whatever happens, we do not want to let the robot go in the bin. And they try and generally pick vertically straight up and down. ActiNav is completely different. We want the robot to dive deep into the bottom, in the corners, with short end effectors. And because we have the path planning, we're allowing the robot to do that. It does it in a collision-free way. Because we're handling all the motion control and it's pre-integrated, your programming is much less. You can write a complete ActiNav program in less than 5 minutes in less than 30 lines of code, as opposed to hundreds, of lines of code with trying to integrate, a camera and a robot. It's not pre-integrated. What's unique is, of course, all the programming is right here on the Teach pendant. So when you get the Teach pendant, the robot programming, the vision programming, it's all in the palm of your hand. Very easy to use touchscreen interface and very simple vision programming. So we are doing CAD matching. So that means in order to, when you have a new part, you put a CAD file, either a step file or an OBJ file, onto a USB stick, stick it in the Teach pendant, and now we know everything about that part that we're going to be picking. So it's very easy on you by using CAD matching. You don't have to train or teach any parts. Just give us that CAD model and then see it. The other thing is teach by demonstration. So there is no simulation tool. There is no offline, programming tool that you need to use. Everything is taught in the real world. The environment is taught in the real world. Pick and place training is taught in the real world. And that means you're not spending your time trying to make the simulated world match the real world. So where was ActiNav the best choice? What applications has it solved? Why was it the right technology? See a few systems here. Let's watch a couple of short videos here.
ActiNav was the first system we were confident we could get in the space available without creating a bunch of extra obstacles. I've been putting the ability of the robot to pick our parts out of the bin, no matter the orientation, and place them on the machine correctly. A task like that is usually pretty hard for a robot to be set up to do.
When we first started reviewing the bin picking solutions, we worked with a number of companies, and we often would send them parts and ask if they could pick them out of the bins, and the answers were always yes, but, and the buts were never acceptable to us. When Universal Robots and Applied Controls first reached out to us with this solution, we figured it was going to be the same as all the other bin picking solutions, where we send them the part and they give us the butt.
We sent the ActiNav team a number of parts, as well as CAD drawings and 3D models of the parts. And within 24 hours, they had sent us 3 different demo videos of them picking each of the parts that we were very impressed by.
We were actually shocked. This initial task for ActiNav was a very simple choice. We have a very old machine that we utilize to cut scallops in a part for firearms. And it takes one operator to sit there the whole time. And it requires a very precise placement to get it into the machine.
The only way that made sense for us to put a robot on a machine tending application was to be able to do randomized. If an operator is to stand there and line the parts all up for a robot to pick them, it would defeat the entire purpose of using the robot to begin with. The cobot has to be able to pick a wide variety of part numbers. It's to pick up oily parts. It's got to be able to pick up randomized parts just laying in a bin. It's to accurately place them so that the machine can process them in a timely and efficient manner. The biggest advantage to ActiNav is that it can just take randomization of parts being dumped in a bin, and as the bin gets low, a person can just come by and dump some more into the bin, and it'll keep picking parts. It doesn't have to be reset, it just keeps picking parts.
So you get to see a few of the part types. I'd say we do about 90% metal parts, brass parts, shiny brass parts, steel parts, aluminum parts. We love cast parts, be machined. And then we also do some plastic parts. You saw the electrical connectors there. Here's a short clip of some brass parts.
We're a New England Union company. We're a brass sand casting foundry and machine shop. When we brought in our first UR10E, we set it up with a palletizing routine, and it would pick and place from the pallets onto the gantry system of the machine. The longest run that we had with the palletizing routine lasted about 8 hours after our shift. Advantages to the ActiNav system is it's a bin picking system, so we can just bring a bin right over to the machine, set it up, and it will just start picking right from the bin. At the end of the day, we make sure that the bin's full, check the standard, and we can leave.
There's enough parts that fit in that bin where we don't have to worry about it stopping at 11 o'clock at night. You can run all through the night, come back to the trucks. It's a beautiful thing.
Here, a few different things that I mentioned. One, you saw the trays with the cutouts, right? And they were about 8 hours of runtime based on their machine. But they really needed longer than that. So the bin was able to hold more parts. You also saw that it took about an hour for them to load up that tray, right? And if you looked underneath the cart that they used, there were 4 different trays stacked under there, so they'd have to change the tray out. And then you also saw the variety of parts there at the end that they processed. They have about 20 different brass fittings that they make there, and they want to process those. The turntable that we were feeding, if that turntable wasn't already there, we would have fed the machine directly. But since it was already there, we just fed that gantry system instead of directly the machine. This is our absolute longest running system that I mentioned. This runs for between 24 and 32 hours, holds more than 6,000 parts. The cycle time's about 25 seconds. It's a steel fitting. It's plumbing or for gas or for engines or something, but it's definitely a steel fitting. It's about a 1x1. This part we're actually picking 5 different ways. We're picking it on the inside both ways. We're picking it on the outside both ways. And then inside half in, half out. It's a little bit like watching paint dry. Cycle time is 25 seconds. But what you see happening here is we're picking them out of the bin, placing them onto that regrip fixture. When the door opens, we're taking the finished part out of the machine, drop it into that bucket, into that finished bin, loading the unfinished part into the machine, and then coming back and grabbing another part out of the bin. ActiNav has built-in auto recovery mechanisms to handle all situations so that it does not stop. What I mean by that is the robot has a force torque sensor inside the wrist. Boy, that's awfully loud. There we go. It has a force torque sensor built into the wrist of the robot. So as we go in to pick, as we monitor that force torque sensor, if for any reason it encounters resistance, it's not going to protective stop and stop the system. It's going to abort, it's going to go back to home, and it's going to try something else. So this allows the system to run unattended for a really long time without stops with these auto recovery mechanisms. And then just one very short one here.
Welcome to our Sherrill facility in Sheffield Group, USA. We produce in these factories high precision engine components and industrial products for U.S. and North American markets.
What I love about this is the new total amount of labor. See, he's got the bag, he's unwinding the bag, dumps the bag of parts into the bin. He's not using one bin, of course, you're using a series of bins.
Once we have the loaded
but that's
bin in
now
position,
the total amount of labor. We're able to go from a 4-shift
it
line
automatically
to a 3-shift
calculates the possible
because now
patches
that
and
piece
routes,
of the labor
after which
has
the
been
robot
replaced.
makes the necessary movements to place the part based on its
Typical
orientation.
cycle times
If the part is
going to be
faced up,
about
the robot
8 to
directly
15
places it
seconds.
to the final location.
And when we talk cycle
and if it
times,
is
we mean
face down,
everything.
it takes it to a
Scanning, matching,
reorientation,
robot
where it is
motion,
placed,
putting the part
repicked,
down,
and then
picking it
placed
up
to the final
again,
location.
and putting it into
Once
the
the
machine
parts
and
are
going
placed in
back
the final
home.
location, it's
This
transferred
customer
to
is
the next
seeing
cell
less than
through a
12
conveyor.
second cycle
And if there are
times
no more
for their
that can be
application.
picked from the bin, the system triggers a bin change sequence and then the robot makes all the necessary movements to change the bin and continue the process with the next bin.
And then our very last one, just you saw this highlighted briefly, but I thought I'd show you it running. So you see actually the sensor is way up top there, about 8 feet in the air, and have this giant tilted hopper. So we work with flat bins, we work with tilted bins, that's not a problem either way. See a dump off mechanism, so if for any reason the part's not oriented correctly, it just gets dumped off. All right. So, kind of what you saw in the videos, why was that the right choice? Unattended, super long, unattended run times, usually a family of parts between 3 and 20 different parts, freeing up labor and, reducing fixturing. Here's, again, some of the parts that you saw as well. Absolutely, the ROI is there. We said it's certainly the most expensive of the 5 technologies. But if you're trying to increase production, you're trying to reduce labor costs, if you have a 30, 45 second processing time and you have to have a person standing there the whole time, it's 45 seconds of cost in every part that you're producing. And we have a nice white paper there we can share. So how can we help you? The best thing to do is these are the QR codes. I guess they're too close together to scan, but we'll get you the links here. You can have a station in mind and answer 8 questions. HTE guys are well proficient as well in ActiNav. They can do live proof of concept right here, or we can get you some feedback and say, yeah, that looks like a really good good application for ActiNav. Looks like it's the right technology. And if it's not, we'll recommend back to you one of those other 4 technologies and why we think that might be a better fit. So, and the best scenario, let us come in and do a site walkthrough. We'll help you figure out what's the right technology for all your machine loading application needs. Yeah, so that's our presentation. Thanks for joining, and look forward to show you the system.
Before we break for that, are there any group questions that you'd like?
Yes.
Have you had any cases with like just flat sheet metal, like maybe like 001 or 009, like shed sheet thickness or anything like that? Any bins picking that kind of part?
Generally, we're picking some type of 3-dimensional brackets. Like we do a lot of brackets. We do some flat parts. How thin are they? I think 1 millimeter is the thinnest. So I got to convert my English to metric, so I'm not sure. But yeah, 1 or 2 millimeters is about the thinnest. Usually the last layer or 2 of parts for very completely flat parts won't get picked. So you get a little lower bin yield, but if your goal is continuous runtime, and they're within that 1 to 2 millimeter thickness, then yeah.
To piggyback onto that answer, there are other technologies that have that. In fact, the next presentation with LMI would give you that depth and ability on flat parts. What this is really ideal for is those 3-dimensional parts like you had talked about. So it is evolutionary from that perspective. A lot of machine tending applications, obviously, that are running that 3rd shift but really don't have the people. This is a perfect product to get set up and run overnight and have your parts back in there. So Eric, thank you very much. We appreciate it. Thank you. Both online and here, we're going to take a break from the presentations. We will be opening up our demo lab. We have the next presentation at 11 a.m. And here was bin picking and flexible feeding. Our next 3D presentation with LMI Technologies or GoCater is more, you can use it with the UR robots, which is great. You can also do some high-end measurement in 3D space. So it's giving you tools to pick the parts. So that's a little bit different concept than what you've heard today. They're all good. You just got to figure out the right way to use them, and that's what we're here for. So thank you very much. We're going to open this up. We'll have the next presentation at 11, break 11:30. That's when we'll be having lunch, and the demos will be open all day long. Thank you.